Good morning. This is the first segment of section 3.1. We are now starting into chapter 3, but before we go really deep into the material, I want to take a minute and kind of talk about where we've been, where we're headed, and have a little kind of side jaunt into discussion about the irrational number pi. So recognize that by completing the last two, the first three sections in chapter 7, that at this point we have all the tools necessary to solve any kind of triangle, not only right triangles, but you know, whatever we have that's that we're confronted with. We know what the requirements are to be able to do that, and we know in certain situations where it breaks down. For example, the ambiguous case of the law of sines. So, purely from the standpoint of the name of the class, trigonometry, the measurement of triangles, I'd say we're done. You know, we can measure every triangle there is. I mean, obviously that's a little naive because there's a whole different class of things that can be done geometrically. And one of them that's really kind of critical is circles. And at some point, probably not in this class, but when you take a calculus class, you may get into something called analytical geometry, where you start looking at different types of objects that look similar to circles, like ellipses and hyperbola and things of that nature. But this is kind of the entry point of that is to start talking about circles in a really sort of concise way. And for the rest of the semester, we will now kind of leave these triangles off to the side and be thinking about angles in a different way. So in order to sort of preface this, I want to talk a little bit about the irrational number pi, which is kind of sitting over here upside down. A lot of people, when I ask this question in class, I will pose it this way. I'll say, what is pi? And invariably, the answers that I'll get is that it's 3.14 something. But that doesn't tell you what it is. That tells you what its value is. And it often takes some time for people to recall that the number pi represents a ratio, and the ratio that it represents is the circumference of any circle divided by the diameter of that circle. And nobody ever when you're learning this stuff in school, nobody ever tells you how to find it, because it's not something that can just be whipped up real quickly using basic elements of algebra. You need to actually have some calculus background. And some pretty severe geometry. So what I'm going to give is kind of a historical context of where this came from. I mean, obviously the use of the number pi is very useful, especially in measurements and things of that nature. You've probably seen people before with these little sticks with wheels on them that have a little counter, and when they measure a distance, you know, rather than pulling out a long piece of tape or something like that, they'll just roll the wheel down the road or whatever else. And there are some theories that suggest that that kind of work, if you will, is one of the reasons why this irrational number pi appears in some of the architecture of your Neolithic structures like the pyramids and some of these other things, is that it was an artifact of the way that things were measured. And it was just sort of convenient, you know, with the pyramids, it's like, you know, this is the height we want, so we'll roll off X number of revolutions of a wheel and we'll call that good. So the first that I'm aware of, and I'm not really a historian, but I do know some things about the history of mathematics. And what I can say is that one of the first kinds of attempts to come up with a value of pi was to break up the circle into equilateral triangles and then say, well, the length of the equilateral triangles is somehow going to give us pi. So let me kind of go through that explanation, if you will. It'll just take me just a second to get over here. So this is section 3.1, page 1. Okay, so consider for a second, and I'm not really a great artist. It's actually kind of challenging for me to draw circles. But imagine for a second that we do have a circle. And one way that we could try to come up with a value of pi would be to break this up into equilateral triangles. So if we kind of have a diameter here, and you've all done this when you cut a pizza. Diameter here, diameter here. Now, if I was a really good artist, you would know that every one of these is an equilateral triangle. So clearly the circumference of this circle is slightly larger than the sum of the lengths of those equilateral triangles. So this is kind of a limiting case. This isn't a lower bound. It basically says pi can't be any smaller than this number. And so if we just arbitrarily pick equilateral triangles with sides equal to 1, right, you'll notice that in this particular case, any diameter is going to be equal to 2, right? And if you just were to add up the exteriors, rather than trying to come up with the actual circumference, let's make this approximately the circumference is equal to, well, there's 6 edges, so that would be a length of 6. Now, because of the fundamental theorem of similar triangles, we know that it doesn't really matter how big or small you make these triangles. Instead of calling them length 1, you can make them length 100 or 6 or some other kind of weird number. But the reality is that the ratio is always going to be the same. And this is sort of an insight into why pi is actually the same for all circles, is that it's the limiting case of the fundamental theorem of triangles. But anyways, so this sort of crude calculation here leads to this idea that pi must be greater than 3. And it turns out that, as you know, the value is about 3.14. This number's pretty good, right? I mean, this is within, 5%? It's 95% accurate. That's astounding for something as simple as this little diagram. Now you could do things where you increase the number of sides, and it turns out that that's actually will get you a number that's even closer and closer. Another example that we could use is maybe instead of we could go backwards, where we have, instead of a series of equilateral triangles, maybe we just do a square in there. And these are all 45, 45, 90 triangles, which we know all kinds of things about. So if we were to set, again, the diameter to 2 and the approximate circumference, well, that exterior is going to be square root of 2. So it would be approximately 2 times square root of 2. Oh, sorry, 4 times square root of 2. Which gives us a pi value that's definitely greater than 2 square root of 2, which, if you numerically approximate that, is approximately equal to, 2.83. I rounded it up a little bit. So you can see with only 4 triangles, we have a number that's not really all that good. When we go to 6, it gets a little better. And if we were to continue this, you will find that you will always have a value that is less than the accepted value of pi, but will get continuously closer. And in calculus, that process is what's called of getting arbitrarily close to a value is what they mean when they talk about a limit. And when you actually take a calculus class, if you do, just remember that this is kind of one of these things that we're doing. Now, this is not a calculus class. I'm not going to explain the idea of a limit to you, but I am going to use this as a means to try to come up with a good value for pi. So rather than actually breaking it up into smaller and smaller triangles, I mean, this was done, I think there was a Chinese mathematician that did this, and I think he got up to, I don't even know, like 256 triangles or something, or maybe it's 210, somewhere in the 200 range, by just separating this up into smaller and smaller triangles and knowing certain things about the different ratios of the sides of those triangles. But we're not going to do that. What we're going to do is look at a circle. And this time, rather than making it a certain specific size, I'm just going to make it, it has a radius of r, okay? And I'm going to break this up into, and I'll maybe write this down, break up the circle into n separate slices. So like I take my pizza cutter out and I just keep slicing and slicing. So when we do this, I'm going to just focus on one of those slices. So here's kind of the arc of the circle, and here's one of the slices. Okay, so remember, there are n of them, right? Well, because this is a radius, each one of those of these these sides are going to be r in length, and we don't really know what the arc length is. But what I'm going to do is I'm going to create a little triangle in here. That's an equal out. That is an isosceles triangle, and I am going to create the altitude of that triangle, which, as we've seen before, that creates a right angle. So now we have two right triangles sort of slapped up together, and this angle and also this other angle up here we'll just call theta over 2. Okay, so that the angle of the the pizza slice, if you will, is theta, but this individual one is theta over 2. Okay, so now what I can say about this sort of this secant length is that well, if you look at this particular triangle, note that sine of theta over 2 is equal to, and we could call this something, but I don't know that it's necessarily needed. But this half of this length, yeah, let's do it. So note that sine of theta is the ratio of the opposite to the hypotenuse. So this will be, let's say the total length is L, then this will be L over 2 divided by R. So there's our hypotenuse, or sorry, our opposite side divided by the hypotenuse. Okay, so we're going to do a little bit of rearrangement here. We're going to have L is equal to 2R sine of theta over 2. Okay, now remember, what's the relationship between theta over 2 and the number of slices? Well, it turns out that we've got the number of individual slices is related to the angle by 300 n times theta is equal to 360 degrees, right? So how many ever we have, we add them all up, add up all their angles, and we're going to get a full circle, right? So note, n is equal to 360 degrees divided by theta. And so we can solve for theta here. We could also, and that's intentionally what I'm going to try to do. I'm going to try to get theta out of this equation. So note that theta then is equal to 360 degrees divided by n. And I'm going to substitute that right up in here. And so this little L is equal to 2R sine, and if you simplify this, you'll end up with 180 degrees divided by n. Now remember, this is just a small length, right, of one individual triangle. The circumference, quote, circumference, is approximately equal to n times L, right? Now notice this is always going to be a little bit less than the actual circumference. But you know, this is an approximation, and as n gets larger, the idea is that it actually gets more accurate. So this will be equal to 2r times n times sine of 180 degrees divided by n. Okay, so let me go to the next page here, because I'm going to do a little bit more arithmetic, if you will, a little more algebra, sorry. So notice that if we take, if you look back at the equation I was working with, now what I'm going to do is I'm going to actually divide both sides by this 2r, right? Now this is still an approximation, but it's a pretty good one. So we've got c divided by 2r is approximately equal to n times sine of 180 degrees divided by n. Right? Now, remember what the definition of pi is. It is, by definition, the circumference divided by the diameter. And notice 2 times the radius is the diameter. So this quantity over on the left is pi. Now, it is approximated by this expression, n times sine of 180 degrees divided by n. Now, at this point, we could ratchet up, I mean, in calculus, you'll do things where you say the limit as n goes to infinity and everything else. But let's just take and pause for a minute and actually show that this equation results in the 2 approximations we already talked about, and then kind of show where it goes. Okay, so note, let's say n equal to 4, and remember that's this situation where we broke it up in, where we broke up the circle into 4 triangles, right? Note that if n is equal to 4, then pi is approximated by 4 times sine of 180 degrees divided by 4, which is 4 times the sine of 45 degrees, which happens to be 4 times square root of 2 over 2, which equals 2 square root of 2. Again, that's that 2.83 roughly that we had right here. Okay, no, it works. It works for 4. What about 6? So n equal to 6, pi is approximated by 6 times the sine of 180 degrees divided by 6, which is 6 times the sine of 30 degrees, which is 6 times 1/2, which gives us the value of 3, like we had before, right? So this is where we had 6 triangles. We get that pi has got to be bigger than 3. This is our approximation. So it seems to work, and there's no reason why it wouldn't. And you know, you can go and work with your calculator and just try ratcheting up larger values, but I'm just going to quote you some results. Okay, so notice that if n equals 10, then our approximation for pi, and I'm only going to, since it's only good to like 3 digits, I'll just write it to 3 digits. So we get a value of 3.09. Now this is a little bit more than 1.5% different. So 3.09, that's a pretty good number to use. If you go by an order of magnitude, say n equal to 100, then pi now is approximated by the number 3.141076. We're pretty darn close at this point, right? I mean, we're out in the 5th decimal place. Because the actual value of pi is 3.141596 something. So we've got 4 digits of significance now. At 1,000, we have pi is approximated by the value 3.141587. So notice we've gotten 1 more digit of significance, and this one's actually pretty close. because like, again, I said it's 3.1415926. So we're within, I mean, we're just really splitting the atoms here. And if you go to say a really big number, like 1,000,000, so if we've broken this this circle up into 1,000,000 different triangles, all of the same size, then we end up with an approximation of pi that is equal to 3.141592654. And for most of you all, this is as far as your calculator will ever take pi out to. So as far as I'm concerned, let's see, that's 4, 8. We've got 10 digits of significance here. Now, if you wanted to go even further, of course, you could keep ratcheting this up. But I mean, this is a pretty good, this is a pretty good approximation. So I will basically say same as most calculators. Okay, so I'm going to leave it at that. We're going to, this, of course, none of this material is in the chapter because the chapter doesn't really do a whole lot of motivation. And this idea of a limit is kind of something that really is foreign to a typical trigonometry class. But we will get started into the main material here in the next segment, which is actually not very long. The whole section is actually pretty short. So I will see you in the next segment.